Well, I've been doing research on the monsoon for many, many years. I started with Monex in the 1970s as a field project, and so I've written a number of papers on meteorology of the monsoon region. So there's been a long-standing interest for over 30 years, and since the TRIM satellite has been in orbit, we've been using it to carefully document the type of rainstorms that occur in that region during the monsoon. It's not, we know it rains a lot in the monsoon, but we were particularly interested with the TRIM satellite and its radar that it has on board, whether we could actually see something about the types of rainstorms that occur. And we've been successful doing that. We've been using about 10, 11, 12 years of TRIM data. It just keeps coming in. We keep adding years. And we've written now about approximately 5 papers just based on the TRIM data alone on the nature of the rainstorms that affect the subcontinent, India, Pakistan, Bangladesh, particularly in the region of the Himalayas, because our particular interest was how the mountains and had an effect on these storms. And what we found in looking at all these TRIM data is that there's a tremendous difference in the type of storms that occur in the western Himalayan region, that is where Pakistan is, which is over a desert, very dry, but near the mountains. It's very different on the eastern end of the Himalayas over Bangladesh, where it's the river delta of the Ganges, and it's basically just wetlands over a huge area at the north end of the Bay of Bengal, and that extends right up to the foot of the Himalayas. So at that end you have the Himalayas next to a big wetland and ocean-like area, and on the west end where Pakistan is you have a desert area. The Indus River comes down from the mountains in that region across the desert, and this is where last year's floods occurred. And since we had been looking at this information for over a 10-year, collected over a 10-year period and written all these papers, we were well aware of the types of storms that occurred there. And we were first of all surprised that we got floods at all in Pakistan, because it is a very arid region. But we were really stunned when we looked at the TRIM data, which luckily were collected for these storms that produced the floods, and saw that the storms that occurred looked like they didn't belong there. They looked like they belonged in Bangladesh. They looked like storms of the type that you see in the east. So this really got us even more excited and interested. And incidentally, I was in India at the time when all this was happening, and watching the reports on the BBC and experiencing all the local interest. So that kind of added to my motivation. I really want to understand what's going on here, especially since we've been studying all of this, and this seems out of character. So we looked even more closely, and we saw that the synoptic situation was very interesting, because in fact it was a low pressure system of a type that occurs regularly over the Bay of Bengal during the monsoon season. But one of these very rapidly moved across northern India and settled into the northern Arabian Sea. So here we have a Bay of Bengal depression sitting at the northern end of the Arabian Sea, and at the same time another new Bay of Bengal depression formed over the Bay of Bengal. So we have these two sort of, one to the east and one to the west, and across the north side of them they produced a flow of this Bay of Bengal type marine air right up into the mountains of Pakistan, right up against the Himalayas. And in these low pressure systems, they're not like mid-latitude lows where you have a widespread synoptic precipitation system. The lows are just favorable locations for mesoscale systems to form. And what was happening was that mesoscale systems like we usually see over the Bay of Bengal were now becoming located over these mountains in Pakistan, because they're this whole environment of Bay of Bengal type air was now dislocated all the way across the continent into Pakistan, and these mesoscale systems were forming there. And these mesoscale systems that form over the Bay of Bengal are different than those that form over the arid west, in that the ones over the Bay of Bengal develop very broad horizontal extents and last for long periods of time, and they contain a lot of what we call stratiform precipitation as well as convective cores. And so we got these broad, wide mesoscale systems with a lot of stratiform precipitation located very, very unusually over the mountains of Pakistan. And they were right over the watershed of the Indus. They sat there for hours just pouring this water out, which is very unusual for that region, all coming down the mountainsides into the Indus. And those mountainsides are also, they're very barren naturally, and they've been brutally deforested. So the runoff was extreme. So you had this very unusual synoptic weather pattern, mesoscale systems of a type that usually occur over the Bay of Bengal, and these deforested mountains, and the end result was one of the biggest natural disasters of recent times. There were more people affected by this event than in the tsunami of a few years ago, plus the Haitian storms, or Haitian earthquake, and the cyclone Nargis. All of those things together didn't even hold a candle to the number of people that were affected by these floods in Pakistan, which was about 20 million people. And another interesting point is that because this pattern was very clearly seen in the synoptic patterns, it was also picked up by the global models fairly nicely. They picked up the basic synoptic pattern about a week ahead of time, and Peter Webster and his colleagues at Georgia Tech have a paper in another journal coming out that shows that they were able to see this potential for heavy rains in the Pakistan region about a week in advance. But there's the further question of why floods, and the why floods is related to the type of storms that ended up there. We got these Bay of Bengal type storms, and they became situated right over these very vulnerable mountains. So very nicely predicted on the synoptic scale, but very unusual mesoscale and convective weather patterns. Yes, they do. Yeah, they do. They run up against the Himalayas and also against the mountains along the coast of Burma. And these mesoscale systems and their stratiform precipitation regions get enhanced by the upslope flow there as well. But I think that not that these are significant events there and they can get flooding and so forth, but these are fairly common there. So I think the people's living patterns and lifestyles and things have adjusted to something where they're essentially out of the way. Whereas in Pakistan, these are so rare that people were right in the path of things. It's sort of like if you built your house, it's in a floodplain because you never have floods there. I do not know about the reactions of the people in Pakistan. I was in India, and I didn't hear. Well, I think everybody was surprised who I talked to. And about a week later, in the same sort of synoptic weather pattern, there was a less well-known but also very important flood in the Kashmir Valley in the city of Leh. And that one was very much a surprise. The people expressed surprise about that one. I was more familiar with that because I happened to be in India. I will say that we do know from Webster's work that the general situation in which there was a lot of rain over Pakistan was not in and of itself an unusual event. I think it was the juxtaposition of these mesoscale storms over a particularly vulnerable part of the mountains that led to this sort of well-predicted potential for precipitation ending up in a flooding situation. Well, the tropical cyclones do tend to move through faster, but they can have, you can get 10, 20 inches of rain from a tropical cyclone overnight. That's probably a little bit more than this. I think the amounts of rain that I saw reported in Pakistan were more like 10 inches per day or something. Same order of magnitude, but the fact that these were anchored to the mountains and sitting in place added to the problem. Just the fact that they were more stationary. They were almost as intense as tropical cyclone rain, but they were sitting in one vulnerable place. The way that works is that the stratiform is really part of the convective system. It's the older convection weakens, starts to die out, and the new convection forms is more active, but the older convection sticks around for a while. And if the environment outside the clouds is moist enough, that stratiform rain sticks around for a long time. And then when this happens, when you get these mesoscale systems with stratiform regions up against this sloping terrain with this anomalous flow associated with these lows just running right up the sides of the mountains, that's enhancing the stratiform. So my hypothesis that's subject to, later modeling and things is that these mesoscale systems had these well-defined, long-lived stratiform components that evolved from the convective part, but the upslope flow enhanced the stratiform components and made them last longer and made them more robust than they would be if they just happened over the ocean or something like that. The convective part of these mesoscale systems that we saw was not as intense as the convection that usually occurs over Pakistan. Pakistan gets some of the most intense convection in the world, but it's usually very local. It happens very quickly. It's very intense. It rains very hard for a short period of time, but the air is generally so dry in the environment it can't sustain itself and build up into a bigger mesoscale system, wider and longer lasting mesoscale system. With all this humidity that was coming in from the Bay of Bengal, these mesoscale systems and the convective, even though the convective towers in them weren't as intense as they would be in a normal Pakistan type situation, the overall humid environment helped these mesoscale systems organize and be maintained over a period of time. That's a good question, and I just have to say we don't know for sure. We do know that mesoscale convective systems in general, when they develop a robust stratiform region, develop a mid-level cyclonic circulation. This is well known, but but whether these do in this region is not so clear. We just don't know, I think, at this point, and we'll probably take some modeling studies and follow-on studies to determine that. There's certainly no observations to answer that question. Well, there's several different types of follow-on studies. First of all, apart from my work, I think the ability to forecast the potential for these events 7 days in advance should be taken advantage of. So far, this has only been done as a proof of concept study over Bangladesh by Peter Webster, and that was in an earlier edition of BAMS back in just recently in November. And they've demonstrated you can do this, but it hasn't been put into practice in this particular region. And I think they could be. But I think what that can do is tell you the general potential for heavy rain. Beyond that, I think we need to use two things: high resolution, finer scale models like so-called cloud resolving models, something of that nature, that are driven by the larger scale models to determine what types of storms are likely to occur in that situation. Are they going to be these potentially devastating mesoscale rain producers or something else? And also that needs to be linked to a good hydrologic model. So a fine scale hydrologic model. Webster's, they do some connection with hydrologic models, but you can go down. You need to do some downscaling to finer scale hydrologic models to actually produce probabilities of forecasting in specific locations. So I think a hierarchy of models and actual application in these regions is a way to go. My own personal research, I'm just interested in how these things work, and our next step we're already acting on is to team up with a group of modelers and try to take the next step beyond the observations and see what these storms were doing in terms of what the models can show us that the data can't.